Very good afternoon, all of you. I'll quickly start. The talk today that I'll present is more around GraphRAGs and how you can kind of integrate this with the entire GCP ecosystem. There are four major sections that I'll cover. We'll go section by section. The first section I'll kind of talk about LLMs as a whole. Then we'll also talk about graphs. We'll talk about RAGs and then finally GraphRAG. So there are four sections. I have limited amount of time, but I'll try to squeeze in as much as I can so that you kind of get the most out of this entire session that we have. So I'll quickly move forward. Cool. I'll quickly start off with the first slide, which is what are LLMs. So I'm pretty sure all of you use Gemini, ChatGPT, Perplexity on a daily basis to kind of to generate text, to generate code, correct? Anyone in the room who doesn't use LLMs in their day-to-day workflows? I'm assuming everyone's using LLMs in their day-to-day workflows. What exactly is a large language model? A large language model is basically a smart autocomplete system that keeps generating text one after the other. So a paradigm shift that happened in case of LLMs is previously good LLMs were based on RNNs and LSTMs. The transition from RNNs and LSTMs to transformers has transformed because you can pass in multiple inputs at once and generate all the outputs sequentially one after the other. So if you look at this particular diagram, when you input a sentence, it's raining cats and dogs, it will kind of pick out the words in the vocabulary with the highest probability based on the input sequence and then generate the next word. Okay, so this is how large language models work. So here is a simpler example. If I have a sentence, if I input a sentence, cat sat on a, with all the words that are part of the vocabulary, it will pick out the word which has the maximum probability and then add that to the input sequence again, then it will generate the next word after the word mat. Okay, so this is how an LLM works. We use LLMs for different use cases. A large language model can be used for summarizing, searching, categorizing an input based on different categories that we define. Then it can also generate new text. So there are various applications that you can utilize LLMs for. You can also utilize it for generating code, creating useful applications that you want to build as well. Say for example, this is a very simple example. If I input just this part of the code that I have, it will generate the final part of the code as well. Today LLMs are so smart, they can generate the entire code base for you. So this is a very simple example that I wanted to demonstrate. If you want to kind of get ideas around a science fair project, you just have to give a prompt and it will kind of give you 10 different options of what you can explore, what you can create as well. And finally, what LLMs help us is LLMs help us prototype ideas into applications very quickly. Okay. Now, how many of you are from college? People who are kind of studying BTech first year, second year, or whichever course you're working on. So most of you, how many of you are interested in AI, ML, joining as a data scientist, etc.? Perfect. So I see 70-80% of the hands up. If there is one research paper that should be your first paper to getting into generative AI, then this is this paper open sourced by Google called Attention is All You Need. This is that one paper that you should start off your GenAI career with or GenAI journey with. This is the paper that was published by Google when Google wanted to kind of carry out a translation task. So Google Translate, have you used Google Translate? Before 2017, the entire solution was not transformer based. In 2017, when this paper became open source, Google kind of showed the way in terms of how translation tasks have to be carried out. So if I have to translate from Hindi to Gujarati or English to French or different languages, right? How does this architecture come into picture is what Google kind of helped us realize. And all the LLMs that you use today, be it Gemini, Gemma, say ChatGPT, Perplexity, etc., right? All the LLMs that you use, the fundamental block of all the LLMs is based on this particular architecture called the transformer architecture. Okay, everyone with me? Yes, no, yes. There are three categories of transformer architectures as well. One is a decoder only model. So all the text generating models that you're using, Gemini 2.5, Pro, Flash, etc. all of these are decoder only models where you only have the decoder section and you pass in input and you generate out output text. Then there are encoder only models. What exactly are encoder only models? Basically, in an encoder only model, you have the encoder section where you feed in an input and you get context aware embeddings or better hidden states of that particular sentence that you have inputted. And then finally you have say encoder decoder models. The model that I was referring to, if you want to carry out translation tasks between two different domains altogether, then you can use an encoder decoder block. Okay, so this is how the entire LLM section is. Now we kind of move to the next section that I want to kind of take you through, graphs. Okay, how many of you use MySQL database? You've written a simple SQL query in your life? Perfect. Okay, with this fundamental basis setup, we'll kind of quickly move towards what graphs are. So graphs are nothing else but discrete set of entities. Each has a set of relationships between two different entities. So there are entities and there are relationships in a graph. We'll quickly move forward as well. So wait. All of you who raised their hands for MySQL, do you know when did MySQL came into existence? 1980s, it's given in the slide. So 1980s is when MySQL came into existence. It was the initial say paradigm shift wherein people can kind of save transactions in form of a database. After MySQL, now is there someone who's noticed a problem by using MySQL? MySQL databases cannot scale really well, right? If your data increases beyond a point, then you will have to add more number of say instances to kind of manage that particular workload, which is where NoSQL databases came along. Do you know any examples of NoSQL databases? MongoDB, anyone else? Cassandra as well, right? CockroachDB is also there. So there are different types of databases which scale really well. But the problem with NoSQL databases is they scale well, but they don't capture relationships as well as MySQL databases. So this is where in 2014, this is where this revolution came about, where you have something called as graph databases, where a graph in general kind of balances out all the disadvantages that you have from a MySQL and a NoSQL database. Okay, a graph DB can scale really well with respect to all the inputs that you kind of feed into, and also the other pieces, it kind of keeps relationships going for that set of activities or the set of data that you ingest. So good for relationships, good for scaling, you kind of have graph databases. Okay, how many of you use Instagram? All of you? Perfect. So if you were given the entire data set of Instagram for 1 million users, and if you have to write a MySQL query to find the friends of friends of friends of friends of friends. So there are 5 layers of friends that you have to find. If you use an RDBMS system, if you look at the last row, the entire activity that was carried out at Neo4j and this particular research paper, this entire execution remained unfinished. Okay, so there was no output that was generated because, again, given the system, whatever system was used in this entire experiment, it couldn't kind of carry out this operation because there were 5 levels of self joins that happened on that particular user ID to find the friends of friends of friends of friends of friends, right? But the same query, if it was executed on a graph database like Neo4j, it took around how much seconds? 2 seconds, and it was able to fetch around 1 million records. This is the power of graph databases, wherein if you have relationships to extract and if you want the scale to be achieved as well, it is here that you can transition over to a graph database. Okay, everyone with me? Now I'll give you some hint in terms of what and how graphs are constructed. Okay, A graph contains two basic elements. There are nodes, there are relationships. Nodes are nothing else but in a sentence, if you are able to discover nouns, those nouns are nothing else but your nodes. Okay, again going back to English classes that we had in 7th, 8th, 9th. So you have nouns and verbs. Your nouns are nodes, your verbs are relationships. Okay, everyone with me? Yes. So just to give you an example, or this is what I'm kind of talking about as well. In these sentences, which actors play in the movie, have I correctly highlighted the nouns? Yes. So actors are nouns because again there are different types of nouns as well, right? Common noun, proper noun, etc. So when you have to construct a knowledge graph from a sentence, your nouns will become nodes and your verbs will become relationships. Now if I have to share this again, relationships again in a graph database are always directional. They start from one set of node, they end at the other set of nodes. Okay. Now how many of you know the simple SQL command? Select star from table and then you apply a condition, right? Now with every database language, you will have some amount of code to write to generate some output as well. In graph databases like Neo4j or graph query language, there is something called as cipher that kind of helps you write that particular set of code. Okay. Before I go to the code part of how this cipher query looks like, if you are kind of convinced that you want to migrate your MySQL database code to a graph database or a Neo4j code, then here is a 1:1 mapping that exists. So all your rows in your relational database are transformed into graphs or nodes. All your joins become nothing else but relationships. All your table names that exist, they become labels to your graph elements that are there, and all your column become properties. Okay, just for everyone's context, do you see this this particular section? Name, email, stars, created at. So when you have nodes and relationships, you can also add key value pairs to every node or relationship that will help you filter out the nodes when you do a search across millions of relationships and nodes that exist. Okay. This is something that I've already completed. But how many nodes do you see in this particular say diagram? 2 nodes, right? This is the hello world code in Cypher. The reason why I'm stressing so much on Cypher as well is because you should have a sense of how the code is written. So this is the hello world code. What you had in select star from table, here it starts from match. And the way I would read this is match all the relationships between the customer node and the product node, which are linked together by the rated relationship. When you buy a product, you are the customer, there is a product. You can buy a product, you can throw away a product, and you can either review a product or rate a product. In this entire exercise, I have a product, I have a customer. I basically want to find out the relationship where I match the customer to the product using the rated relationship. Okay, this is what the first line is. Okay. After you filtered out the nodes and relationships that you are searching for, then you return key and value pairs that are of your interest. Okay, so in the second line you have c.name as customer, p.name as product, and r.stars as rating. When you run this query on Cypher, when you run this query on Neo4j graph database, what you will get are a list of all nodes and relationships where there is a customer, there is a product, the customer has rated that particular product. Okay, so this is how a graph query language looks like. Now, this is a simple graph that I want to show you in a Neo4j graph database. This is a very small graph, but it looks very big. How many of you have seen the movie The Matrix? In the movie Matrix, there are multiple people who have contributed differently to the movie. There is this person who has kind of acted in the movie. this person has also acted in a movie. For a person, you can either act in a movie, direct a movie, produce a movie, and you can do different things to a movie, right? All of these relationships are captured in this particular graph that you see here. Does this make sense? Perfect. Now I'll quickly go to the third section. I'll quickly check the time as well. 3:24. We are well on time. So what are the 4 sections that I had to cover? Anyone? LLMs, graphs, RAGs, and then GraphRAGs. So we are at the third section right now where I'll talk about RAGs. I think there was this question around RAGs as well. What exactly are RAGs? Hopefully by the end of session you will have a sense of why RAGs exist. Even if you don't understand the nitty-gritties of RAGs, you will still get a sense of why RAGs are so popular in the AI domain. Okay. How many of you have a bank account? How many of you download your bank statement every year, every month to check everything is in place? Perfect. How many of you never uploaded your bank statement on Gemini, but if you ask a question and if you're very lazy, if you want to find out what is your total expenditure for a month, you download a PDF, you never upload it to Gemini, or you never upload it to ChatGPT. All you do is you keep the PDF with yourself and you ask, hey Gemini, can you tell me what is my last month's expense for a particular activity that you had performed? Is Gemini or any LLM capable enough of giving you that answer? Why no? So I hear everyone saying that say the LLM does not have context for it, right? RAGs exactly are what you say right now, which is if you want to get answers to private data that the LLM has not been trained for, it is here that RAGs come into picture. RAGs help you give that context to the LLM and then the LLM generates a response. Okay. Now I want to give you that thought, which is where we can kind of get through this idea of what RAGs are and what GraphRAGs are. Okay, I have a use case with me. I have 1000 PDF documents containing, say every PDF document is a 2-page document, and I have a small biography of a Nobel Prize winner in that one document. Okay, let's assume there are a total of 1000 Nobel Prize winners. I want to create a system that is able to answer queries on those 1000 PDF documents. Okay, so it is here that I start off my discussion with RAGs, right? So this is the typical pipeline of how a RAG system looks like. Okay, so you have the retrieval, firstly the ingestion section, then you have the retrieval section, and then the synthesis or the generation section. Okay, now what happens behind the scene when you create a RAG application, right? The first thing that you have are documents. How many documents do we have? 1000 documents. Every document is a 2-page document. The content inside it is a short biography of a Nobel Prize winner. Now what I have to do is, if I'm given this particular document, the first thing that we do is there's something called as chunking, right? Chunking, what it does is it kind of breaks down the document into multiple smaller sections so that the LLM can basically process that data that comes in, and then it's able to generate the responses as well. So the first piece is chunking. So if I have 2 pages, I'll chunk it to maybe 10 odd chunks or 10 small sections which are part of the same document. Okay, there is something called as overlapping chunking, non-overlapping. There are various other techniques, we'll not go there, but the idea is to break down this entire document that the LLM has never seen and generate chunks out of it. Okay, now once the chunking activity happens, there is a process called as embedding generation. How many of you know about embeddings, heard of it? For all of you who have not heard of it, whatever chunks that you create, right? If I have a 2-paragraph, if I have 2 pages, if I have 10 paragraphs with me, I want to convert them into vector representation. Okay, when I say vector representation, it's just a fancy way of creating a list of numbers that help the LLM understand what the context is all about. Okay, again, embeddings, going into depth will be a bigger discussion, but the idea that you have to remember is for every chunk that you create, LLMs cannot process words as it is. You have to pass context somehow the other to the LLM, right? Which is where what you do is you kind of create vector representations, which is called embeddings, and you save it into something called as vector databases. Have you heard of vector databases before? There are a lot of popular vector databases like Quadrant, Pinecone, etc., right? So all of them are gaining a lot of popularity. All of these vectors are saved into this vector database. Now when a query comes in, right? When a query comes in, the query is converted into a vector representation format. This vector is searched against all the numbers that I have. Do you know about cosine similarity? Cos 0 is how much? 1. So when two vectors are same, the angle between them is what? 0. Cos of 0 is 1. So what happens here in case of RAGs is, when you have the input which is very close to that small paragraph that you have saved in form of an embedding, you pluck out 5, 7 or 9 similar chunks based on the query, take those chunks that are very similar to the query, pass it to the LLM and generate a response. That is how a typical RAG pipeline works. Is everyone clear about this? Yes? Yes? Perfect. So now this works really good, right? When you have queries, you get all the top matching chunks and then you pass it to the LLM for generating a response. Works really well. I built this system, it works really well and I get really good answers. Now I go forward to the last section of the talk that I have, which is GraphRAGs. I ask a simple question to this particular system that I've built. How many Nobel Prize winners are from United States of America? Okay, my question is very simple. How many Nobel Prize winners are from United States of America? For every biography that I have, there is some mention of the country of that particular person. Okay, now for this response to come out, if you go back, this top K value that you have, right? This value is constrained to around 9, 11, 13, right? And the exact number in terms of Nobel Prize winners from United States of America is more than 400 plus. Okay? Now, if this query is what is asked, my top K value is 11, for example. It will pluck out 11 chunks from different documents and it will generate a response that the total number of say Nobel Prize winners from US are 9, 10, 8, depending on how many unique chunks it is able to pluck out from different say biographies, right? Now how do we solve for this? It is where here there is something called as GraphRAG that comes into picture. Okay, so GraphRAGs give that relationship or give that context even further to the LLMs so that it is able to kind of generate better responses, keeping the relationships intact. Okay, again we started off the discussion with normal LLMs, then RAGs, graphs. The reason why graphs grew in so much of popularity is because it can scale really well, plus it can keep relationships really well. And then we discussed about RAGs. Now we'll discuss about GraphRAGs. If you see this diagram, this is the original first implementation of GraphRAG by Microsoft. Again, entirely open source. You just have to search for GraphRAG Microsoft and you will get this particular open source repository. Now the way this works is, if you look at the diagram, the first initial steps are very similar to our traditional RAG system, right? There is something called as text chunk generation. There is no embedding that is generated here. There is something called as entities and relationships that are generated here. Do you now recall what this entity and relationships are? For all the sentences in the document, those sentences will be converted into nodes and relationships. That is where entity and relationship diagram formation comes into picture. All of that nodes and relationships that are generated will flow into a knowledge graph, and there is something called as a community detection algorithm that I'll come to. All of that is generated over the fly, and then you have the final response generated. So now if I go forward, so this is the process of firstly how chunking happens. this is the entity extraction diagram. Do you see this particular 2-3 sentences? For these 2-3 sentences, do you agree that these are the nouns that are there in these sentences? Yes, no? Yes? Yes, no? For all of these 2-3 sentences that I have listed above, do you agree that these are the nouns that exist for these particular sentences? Yes? These are the relationships and these are the entities that are formed. So entity relationships is what is formed. There are nodes, there are relationships, and then you have entity and relationship mapping. Now once you have this, you create a knowledge graph and you push all of this knowledge graph into a graph database like Neo4j that can scale really well. Now there is something called as community detection algorithm. How many of you have this subject called clustering? Have you heard of clustering before? Think of community detection algorithm as a form of clustering where you define what the cluster has to be at the top level. So you can have a top level cluster, then you can have a cluster below that, then you can have a cluster below that, and you can keep going till the time you have multiple clusters that you are interested in. Okay, so your community detection algorithm basically creates clusters based on top of nodes and relationships, and you can keep increasing the complexity as well. Now once you have this, how do you create clusters is where Gemini comes into picture. So all your entities and relationships that you have created, you just have to take all the entities and relationships and pass it to Gemini, create a better suited prompt for this particular activity, and create proper communities or high level say clusters that can kind of give you that data, right? Now there are I wouldn't go into depth of this, but what happens is there are two searches that happen in case of a GraphRAG algorithm. One is at a global level, the other is at a local level. Now a global level search happens at the community or the cluster level, where if the answer that you're looking for is present in the community level itself, it doesn't go into the sub community or the sub cluster level. It takes the context from the upper level, passes it to the LLM and generates a response. This is a global answer. Okay, so there are two searches or answers that a GraphRAG system produces. One is global, the other is local. Global is at a community level or at a cluster level. Local is at a community plus sub community level. How many of you know MapReduce? Something that is very popular with Hadoop. Heard of it? Yeah? Basically, the way GraphRAG filters and finds the right context through subcommunities or clusters is through this particular MapReduce kind of a terminology itself, where you have the top level cluster, then you have subclusters, and then you have sub-subclusters. Wherever it requires you to filter out the right set of indexes and relationships, it kind of discovers that, takes that context, passes it to the LLM, and the LLM finally generates this response. There was some activity or there was some amount of testing that was done with respect to normal RAGs and GraphRAGs. This is a data set that no LLM has been kind of taken. I mean, this data set has never been used for any LLM training, which is where when a question was asked, can you give out the themes of, can you give out the top 5 themes of this particular data set? This is the difference between the responses that you observe. So so I have 5 minutes, which is where we are almost at the end. So you have your typical, so left hand side is a typical RAG response, which is not very comprehensive. Right hand side is where you have a classic GraphRAG example where the graph is able to generate really good context because of the search capabilities that it has, the relationships that it has, and accordingly it kind of gives out the right relationships. If you've read this entire, or if you've learned all of this graph piece so far, here is your chance to grab a t-shirt so you can all pull out your cell phones. You have to go to graphacademy.com, which is something that is given in this particular QR code. if you have understood a little bit about how graphs work, you can pick up this certification. There are multiple certifications available on the Neo4j website. You just have to scan this QR code, go to the site, register. You can take up the certification. The good part about this entire activity is the certification is free of cost. You don't have to pay money to apply for a certification. Once you are certified, you will get a t-shirt delivered to your home as well. So this is a t-shirt that exists at this point of time. And finally, there's an annual conference that's happening for Neo4j that happens every year called Nodes. You can kind of scan the QR code again and get this, join this virtual conference. Again, you don't have to pay any money. You just have to log in to this entire day-long event that happens and learn more about the different advances that are happening in graphs as well. Okay? Cool. Thank you so much for your attention. This is all that I wanted to cover today. I hope this entire session was insightful. Thank you.